Hello, and welcome to our lecture on the first law of thermodynamics and thermodynamic processes. Okay, so in the key terms, I'm actually going to focus on the processes, and we'll see the first law show up in the equations. Okay, there's a lot of ideas to unpack here, but they're all very connected to one another, so there's a cohesive picture, but we do have a lot to do. All right, so the first law of thermodynamics and thermodynamic processes, it's all about energy. It's all about pressure and volume. We're going to be using the ideal gas law. This is very much a thermodynamic idea, right? It's building on all the ideas of heat and internal energy that we've been discussing about so far. And like I said, certainly the ideal gas law is going to be prominent in our solution methods and in the concepts. All right, so this is all about heat flow. Let's understand what that is. How do we make sense of it? How do we apply it? And once we finish this lecture, hopefully that will all have come together. All right, so first of all, our first key term is a very important one. Obviously, I've left a lot of space for it. That is the PV diagram. All right, now the PV diagram is this. It's really a graph. It's pressure as a function of volume. That's the P and the V, pressure and volume. Okay, so that's it. It's simply a two-dimensional graph. Now, one big thing we're going to consider with the PV diagram are a few very common and characteristic processes that are represented on the PV diagram. So essentially, moving from one point, say point A to point B, how are we going to do that? Are we going to take a path like this, right? Are we going to take a path like this? You know, what path are we going to take to go from a certain pressure and volume to a new pressure and volume? Because obviously, there's a lot of systems, important physical systems, where heat is exchanged with that system and that system's pressure and volume change. Okay, so that's what we're talking about. How do we go about considering those types of phenomena? All right, well, let's consider the big four. Okay, there are four very common, that's not an exhaustive list, but very common processes, which are called the thermodynamic processes. Okay, and they all involve going from some pressure and volume value to a new pressure and volume value. All right, so the first one is called an isobaric process. Isobaric means constant pressure. All right, so here's an example of an isobaric contraction because look at the direction. It's drawn with a little arrow showing that it's going backwards along volume, so the volume is decreasing, hence contraction. All right, you could also have an isobaric expansion. Now we have isovolumetric heating. Okay, we're going up this way, okay? And that means we're keeping the volume constant, hence isovolumetric. Iso means constant. The heating part is a bit harder to understand because you might be thinking, well, you're increasing pressure, but how do we know that you're increasing temperature? Well, the ideal gas law, PV equals nRT, all right? If you keep the volume constant and you increase pressure, what must go up? T. And you might be like, well, N could go up. Obviously, R can't because R is just a constant. N could increase, but N can never increase. The types of systems we're considering, and I'm going to specify this on the next page, are closed systems, which means that they exchange energy plenty with the outside world, the environment, but they don't exchange mass with the outside world. Thus, the number of moles in your system always remains constant. Okay? All right, so this is isovolumetric heating. Then we've got isothermal expansion. I bet you can guess what isothermal means. It means constant temperature, okay? And so notice that constant temperature, unlike the other two, is actually a curved line, all right? Because it turns out that to hold the relationship of pressure and volume when temperature remains constant ends up being a curve. Specifically, it is a logarithmic curve. We're not going to prove that, but I'll give you the formula that shows you the area under the curve, okay? But the important thing is that it's curved, okay? All right? And I should say that the area under the curve is logarithmic. It is a reciprocal curve, okay? But this is a curve at constant temperature. So any point along here would all have the same temperature. That's what it means to be isothermal, all right? Now to explain the last and final of the common thermodynamic processes, I'm going to add another one of these isothermal ones, all right? And of course, the one I showed is expansion because volume's increasing. But let's show another isothermal one. This one's going to be isothermal contraction. Typo there, that should say contraction. I probably just copied it over and forgot to change it. So it should say contraction instead of expansion, because here we're going in a decreasing direction of volume. But the reason I drew a second isothermal process in is to show this blue line here, because this blue line represents adiabatic expansion, okay? And the idea with adiabatic expansion is that what's happening is the substance is expanding in an adiabatic way. That word isn't so obvious, right? What does adiabatic mean? Well, adiabatic means constant entropy, but we won't get to entropy until a little bit later. So the best way to think about it is no heat is exchanged with the outside world, okay? So it's the closest thing to an isolated system, okay? Of all the types of processes we talk about here. So during an adiabatic process, your system is, at least during that process, isolated from the outside world, okay? And the thing about adiabatic expansions, or any adiabatic process, contractions as well, is it passes from one constant temperature curve, which is called an isotherm, so I'll define this in a second, to another constant temperature, okay? And in this case, what is going to happen is that as you expand, adiabatically, your temperature will have to decrease. So it's actually another change I'm going to have to make before I upload these, is that this line here should actually go from higher temperature to lower temperature. So this blue line, I show it going from lower temperature to higher temperature, all right? But it should go from lower to higher, all right? Because T1 is a greater temperature, because as we move in this direction, temperature increases. So temperature increases in the direction of the arrow that I just drew. And so that means that this expansion, if it was a contraction, it could be going that way. So I could either change this to a contraction and show it going in the direction it's going, or the curve it's going, we might put an arrow there, or I can have the blue line go like that. So I'll fix that before I upload it, okay? All right, so that's two changes I need to make to this diagram. So please take note of that, okay? But otherwise, lots of important ideas, and we'll get lots of practice with them, okay? So a couple other bullet points. The best way to a PV diagram is the best way to visualize thermodynamic processes. I usually don't make quality claims like that, but it really is. It's super helpful. Okay. The pressure measured in pascals is a function of volume. We mentioned that. That's the whole idea of the graph. And the curved lines of constant temperatures, they have a name. They're called isotherms. The reason we give them isotherms is because the idea is that, like, if you think of like isobaric contraction, you're crossing isotherms, right? So you're going in the direction of decreasing temperature because you're crossing all of these isotherms. And all the isotherms are these curved lines, almost, not to make things confusing, but it's almost like a third dimension, right? Because essentially what these represent is that if you were to graph temperature on like a z-axis, then you would, that's kind of what we're representing, that superposition of that data with these curved lines, okay? All right, so let's quickly summarize the four processes that I drew in the diagram. So first one, any heat flow, this is an isothermal process, any heat flow process in which the temperature remains constant, okay? So you can still have heat entering the system, but that means that the internal energy can't change because the temperature doesn't change. Because remember, internal energy, or a change in internal energy, was 3/2 nR delta T for an ideal gas. And we're always going to assume that the thing that's undergoing these processes is none other than an ideal gas. So that means that in this case, if no temperature change, your change in internal energy will be 0. Okay, so that's isothermal processes. All right, next up, the isobaric, that's the horizontal line. Here, any heat flow process in which the pressure remains constant, and you'll see the consequences of that. Isovolumetric, any heat flow process in which the volume remains constant. These are usually the easiest to solve. And then finally, the adiabatic process, any heat flow process in which there is no heat flow, so Q equals 0, because after all, remember Q represents heat flow. This means no change in entropy, a term we'll define in 2 lectures. Okay? All right, so there's our terms, there's our diagram. Let's move on to some tables that summarize how we make sense of these processes. Okay? So I've collected these tables from 2 different sources. I haven't kind of recreated them myself yet. It's on the to-do list. But the important thing is that they're wonderful summaries of how to kind of make sense of the processes that we just saw on the PV diagram. They're wonderful references in that regard. But we do have to acknowledge that they have a change in convention between them. So first of all, I'll zoom out just a tad, okay? So this first one, it labeled the first law of thermodynamic processes for ideal gases. Okay, that's great that it specifies ideal gases, but all of my examples will be ideal gases. So you can be confident that every time you're going to see a thermodynamic process, or you're going to see a heat engine, which we'll discuss in the next lecture video, it's always going to be an ideal gas. Okay, and here are the processes: the isobaric, the adiabatic, isovolumetric, isothermal, and then just general. Okay, now here's the thing. All right, for an isobaric process, the change in internal energy is represented by this. N is the number of moles, CV is actually the specific heat, and delta T is obviously the change in temperature. So this is actually fascinating. This is telling you there's this relationship with isobaric. There's a change in internal energy, there's also heat flow, and there's work being done, okay? And so isobaric is the only type of process where none of these three terms, change in internal energy, heat flow, and work being done by your substance, are zero, okay? So it's a good one to take note of. Another thing to take note of is that in this column here, this is the work being done on, notice the subscript, the ideal gas. It's not the work being done by the ideal gas, but rather it's the work being done on the ideal gas. And that's going to make more sense in just a moment when I talk about the first law of thermodynamics. All right? But if we go down here, in this table, which is also a good summary and one that doesn't rely on ideal gas, the ideal gas law, in that it doesn't have any moles, doesn't have any specific heat values. Instead, it's just a more general idea about what is being held constant and then what is a consequence when we consider the first law, okay? The first law of thermodynamics, that is. And by the way, here it is. Here's the first time you've formally seen the first law of thermodynamics. You're going to see it just below in the key equations, okay? And if you look here at the first law, it says the change in internal energy equals the heat minus the work, okay? But here, the work term, instead of being the work being done on the gas, is the work being done by the gas, okay? So it's just an important distinction because you can either subtract the work being done by the gas or you can add the work being done on the gas. Both effects are the same. Why? Well, because work on the gas is the same as negative of work by the gas. And that's just simply Newton's third law, right? Equal in action, reaction force. Equal in magnitude, opposite in direction, reaction force. If the gas pushes on the outside world, then the outside world pushes back. And when we're talking about a gas doing work, the way you should think about that, the way you should actually have a practical understanding of it, is think if you heat up a chamber and that chamber expands as you're heating it up, then it has to push the air out of the way to expand, right? Or a balloon that's heating up and expanding. It's pushing the air out of the way. That's doing work on the outside environment, okay? Another really good example of work being done on or by a gas is like a piston chamber system. Imagine like a chamber with a gas inside. That gas is heating up or getting pressurized, or there's some sort of change in that gas, and that's pushing a piston. That's like in the engine of a car, right? There's gas trapped in a chamber, the combustion chamber, and then that pushes the piston, okay? So that's the idea of the gas doing work on the outside environment, on the outside world, okay? So that's what we're talking about. That's why work is being discussed here, because gases can expand or contract, and then they do work, okay? Furthermore, the concept of work we can see right here with isobaric. Work is simply equal to pressure times the change in the volume. And then notice this, in the general expression of thermodynamic processes, the work is equal to the PV area. It's the area under the PV curve, okay? So you're going to see that in an example, but just to elaborate on here, that'd be the idea that if I was to trace the area under this isotherm, okay, and I'll shade it in, that area is the work, okay? Either the work on or the work by, depending on the direction, right? Depending on whether it's an expansion or contraction, all right? Now the reason with constant pressure processes, with isobaric thermodynamic processes, the reason that it's simply multiplication, simply pressure times change in volume, is because it's a rectangle. And since pressure is unchanged, the way to find the area under this curve is simply this value of pressure times the width of the rectangle. Okay, so that's the only process where it is so simple to find the work. I guess the only other one that's of comparable simplicity is the isovolumetric, where the work is zero because you can't have any area under a vertical line, can you? Okay? Okay, so again, wonderful reference here, wonderful summary of both these tables. They're both very helpful. All right, I probably find myself using this one a bit more, but they're both good references to kind of remind yourself of how the first law works. But now let's see the first law down below in key equations. Okay? Okay. So here we have the first law of thermodynamics. Okay? I probably should have made it a key term. I didn't realize that until after the fact. But here it is expressed in two slightly different ways. What is it? Well, it's an energy conservation laws. It is an energy conservation law for closed systems, okay? And what I mean by a closed system, scroll down here, a closed system is any system that exchanges energy but not matter with the environment. So unlike an isolated system, which neither exchanges energy nor matter, a closed system does allow for the exchange of energy. Heat can flow in and out. Work can be done on or by the system, but there's no change in matter. So the number of moles of your substance inside of your system is unchanging, okay? So here's what it looks like. Here's what our conservation of energy equation looks like, called the first law of thermodynamics. It says that the change in internal energy, delta U, is equal to the heat added to the system, okay? And this would be the change in internal energy of the system, minus the work done by the system. And that makes a lot of sense because this is kind of how much energy you're adding. Okay, this is what the system has to work with. If the system itself heats up, then that's going to, some of the energy is going to go there, right? And then if the system does work, then that's also going to eat up some of the energy. Because if you think about it, we could rewrite this as Q2 equals change in internal energy plus work by, right? So you add heat to the system, you can get an increase in internal energy, and that system can do work on the outside world. Okay? But if you heat up more, then you have less work to do. If you do a lot of work, then you can't heat up as much, right? So you have to balance the two. Okay? So that's when you write the second term, this work term, as work done by the system, by the ideal gas, by the chamber of trapped gas. Okay? Because that's what we're talking about here. We always think of it as a chamber of trapped gas. Okay? All right. On the other hand, you can write it as change in internal energy equals Q2 plus work done on. Okay? Because in this case, if you're say compressing something, then this would be a positive term. And then if you're compressing something and heating it up, like you're compressing something and putting it over a flame, then the combination, so you see you're adding them together, would increase the internal energy of the substance. So kind of it just depends how you want to think about it. Okay? So these are both valid ways of expressing the first law of thermodynamics, okay? All right, now in reference to the table above, the table that has all of the, that is derived from the ideal gas law, okay? Well, really is a combination of the ideal gas law and the first law of thermodynamics, is, we see all these terms, CV, 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 CP. Well, what are they, okay? Well, for an ideal gas, okay? First I got some other labels here. So change in internal energy is delta U. All right, Q is heat added to the system, and then work here, this is work done by the system on the environment, and then this one is work done on the system by the environment. See? Prefixes are so important. On, by, on. Okay? All right, but now on to what's CV and CP, okay? So CV is specific heat. Remember specific heat when we talked about, say, calorimetry, okay? So this is specific heat for an ideal gas at constant volume. Okay, so this is a constant that applies to ideal gases, and it turns out that CV for ideal gases is always 3/2 R. So it is a value that is exactly equal to 3/2 times 8.314 joules per mole Kelvin. Okay, that is the specific heat, right, in molar form of an ideal gas. Okay, for an ideal gas is at constant volume. Now, to be fair, this formula or this expression, this term, shows up in situations where the volume is not constant. Case in point, if you look at the table above, look, it shows up for isobaric. That's definitely not constant volume. It shows up for the general case as well, all right? And even shows up for adiabatic. So it ends up being like it has a broader application, although to be fair, it does also show up under the actual isovolumetric process. So sometimes it's combined with other systems, okay? So it's a bit of a misnomer, but this is the way you'll always see it listed as the specific heat of ideal gases at constant volume. And the other one, the counterpoint, is this one here, C sub P, or CP. I bet you can guess, it's specific heat of an ideal gas at constant pressure. And it's just equal to CV plus R, which means it's 5/2 times R. So they're actually just constants. They are actually constants, all right? They're not something you have to look up in a table. They're always 3/2 R and 5/2 R, okay? That's it, that's what they are. Now, you might wonder then why not just give them a numerical value? Well, because in this class, we're focusing our attention on ideal gases, but we might want to talk, say, about diatomic gases or other gases in another context, in another class or another discipline. And that's why in that case, you would have different values. So maybe for some other type of gas, instead of 3/2 R, the specific heat at constant volume for a diatomic gas might be 5/2 R, in which case this one would be a 7/2 R. So that's the idea, is they can change for different types of gases, but that's beyond the scope of this class. Okay, so for us, CV will always be 3/2 R, and CP will always be 5/2 R. Okay, All right, so the next one is also going to be values that tend to always be constants. And this whole set of 4 equations here is all for adiabatic processes, okay? Turns out it gets a lot of equations, okay? It's also, if you haven't noticed, it's the strangest one to wrap your head around. But again, it will make more sense once we cover entropy in a couple lectures, okay? So what this says here is that pressure times volume, and then, well, pressure times volume raised to the gamma power is a constant, okay? What does that mean, right? What's pressure times volume to the gamma power, right? What's gamma, all right? Well, turns out that this is the conditions for adiabatic processes. So the idea, and I'm not going to derive it here, but the idea is that pressure times volume to some power will be a constant for an adiabatic process. That steeper curve on the PV diagram, that curve that crosses isotherms, okay? It's the only other common isothermic process that's a curve. So the two that are curved are isothermal and adiabatic is the one that's steeper, okay? And the derivation, the math behind it is that the product of pressure and volume to a certain power is always a constant, okay? And then we could also replace pressure with basically temperature, and then temperature times volume to that same power minus 1 is a constant. And this substitution just comes straight out of the ideal gas law. So to go from here to here, you can prove it to yourself, I'm sure, is just comes from the ideal gas law, okay? But I wanted to show both in the key formulas, all right? And then what is gamma? So gamma is the adiabatic index for ideal gases, okay? And gamma, by definition, is just Cp over Cv. So it's just the specific heat of an ideal gas at constant pressure over the specific heat of ideal gas at constant volume. So in other words, it's 5 halves R over 3 halves R. The R's just cancel, and it's just 5/3. So gamma is just 5/3. That's it, right? We could just replace it with 5/3. So that's all. Again, the only reason we don't just say gamma is 5/3 and even show where it comes from is so that this could be applied to other gases, okay? All right, and last, we have the work done by an ideal gas, okay? And that's the work done by an ideal gas or the work done on an ideal gas during an adiabatic process, that process where no heat is exchanged, okay? All right, so that's this formula here. The work done on, the way it's written, so since it has no negative in front, it is on. So the work done on an ideal gas during an adiabatic process, all right? So this is one of our more unusual work formulas, but it ends up being pretty easy to calculate because it's just 1 over gamma minus 1. Remember, gamma is just 5/3, so then this would just be 1 over 2/3 times P1 V1 minus P2 V2. And then you can even clean up even more and take the reciprocal of 2/3, which just becomes 3 halves. And so then this just becomes 3 halves times the difference in the products of pressure volume. Okay, so that's the work done on an ideal gas during an adiabatic process. Okay, now everything, all of this, except for this formula is in your book. Your book, for some reason, did not decide to include this work formula. It tells you to estimate the area under a curve using rectangles for adiabatic processes. But this is not a terribly complex formula, so I'm giving it to you so we can use it for some very few problems, okay? And actually, while we're on that note, I want to show you the other unusual work formula. I think I meant to call attention to it a bit earlier because I have it up here labeled. This one is the other kind of weird work formula. This is the work done on an ideal gas during an isothermal process. And that one has a natural log in it. And again, every time we talk about work in a PV diagram context, it's always the area under the curve, every single time. It is literally, unit-wise, it's got the units of joules, because pressure times volume, think about the units. Pressure times volume gives you joules. Okay, pascals times cubic meters, that's joules. Okay, because it's Newton meters times cubic meters, right? That's joules. Newtons per meter. Pascals are newtons per square meter times cubic meters, then you get Newton meters. Newton meters are work, okay? I'll write it down, all right? So the idea, right, because Pascal is pressure times cubic meters, okay? Pascals are newtons per square meter because it's force per area times cubic meters, okay? So then you cancel out some of the, most of the meters and you're just left with Newton meters. Newton meters are work, right? Newton meters are joules, okay? That's why we can be so sure that the area under the curve of any curve on a PV diagram is work, all right? But anyway, the area on an isotherm is defined by this formula here, all right? So those are the two oddball ones, adiabatic and isothermal. Those are the ones with the strange formulas that you have to use if you want to calculate work. All right. All right. Well, that's enough introduction, I think. let's get on to some practice problems. All right, so I have 5 types of practice problems, okay? Because we've got a first one, which is just general thermodynamic processes. Our second one is isothermal. Our third one is isovolumetric. Fourth one is isobaric, and the last one is adiabatic. All right. So I wanted to separate them out so you can really be like, oh, this is one of those. This is one of those, right? So really, these are all the types of processes, and each one is going to get its own example. All right. I think I have 2 examples of the of isobaric because it's one that can kind of involve more steps potentially. And so, but they're all going to get a little bit of attention, and you can all do more of them for your own practice. Okay. So first, let's do a couple that are a general thermodynamic process that doesn't fall into any of these common categories. All right. So let's look at these 2 PV diagrams, right? So pressure as a function of volume, 2 examples. And we want to find the numeric value of the work done on the gas in figure A and figure B, okay? So the work done on the gas should be the area under the curve. But the question is, will it be negative or will it be positive, okay? Well, first, let's have an intuition here. This process that's shown in figure A, well, it's an expansion because look at the direction. The gas is expanding, it's getting bigger. So that means that the area under the curve should represent the work being done by the gas, shouldn't it? Right? Because the gas is pushing on the outside world. So this value is positive if the gas is doing work, okay? On the other hand, if we look at figure B, in this case, we've got a couple of rectangles, right? In this kind of weird stepwise process, go down there. And what's happening here? Well, the gas is contracting. Well, if the gas is contracting, that means the outside world is doing work on the gas. So this value, this area under the curve, it should be positive as work being done on the gas. Okay? All right. So first, A, work done on the gas is the negative of the area. And then we find the area by simply taking a triangle and a rectangle, or this is the triangle and that's the rectangle, all right? And we get a value of negative 4 times 10 to the 5 joules. Okay, so that's the numerical value of the area under the curve, and it's negative because the work on the gas is negative. Do you see it? Okay, and then in B, the work done on the gas is positive, okay, because the outside world is doing work on the gas. And then in this case, we just take the area of the 2 rectangles, the one short and the one tall, and we get 3 times 10 to the 5 joules, or 300,000 joules. All right, and then in C, I asked for the work done by the gas in A and B respectively, okay, for C and D. And so since C is just going to be the negative of the answer for A, which is positive 400,000 joules. Because of course, right? In this case, of course, work being done by the gas is positive because the gas is expanding, all right? Just the same reason that the work being done on the gas in figure B was positive because the gas is being pushed into contraction. And then finally, if we want to find the value of the work being done by the gas for figure B, then it will be negative, right? And I know that's a little bit strange because we don't normally think of of the work being done on the gas being negative when the gas is expanding. We just think of the work of the gas doing positive work on the outside world. So we tend to focus on the positive, not the negative. But sometimes we have to be able to switch the signs to make sense of the problems that show up with these thermodynamic processes and PV diagrams. Okay? All right. So let's move on to the next example. Example 2. This is going to be another general one, right? Because this doesn't fall into isobaric, isovolumetric, isothermal, nor adiabatic. Right? This is some weird linear one going from point A to point B. All right. But it's nice because we can find the area under the curve. That's the value of the ones that are linear, right? Because it's a triangle after all. And let's read the problem. So a quantity of 4 moles, so in this case I'm actually specifying the number of moles, of a monatomic ideal gas expands from an initial pressure, and I left it off as a typo, of 100,000 pascals, an initial volume of 1/10 of a cubic meter, to a final volume of 3/10 of a cubic meter, and pressure of 2.5 times 10 to the 5, or 250,000 pascals. All right, and that's shown in the figure. And by the way, I left it out of the text of the problem, but it was always shown in the figure, all right? And compute the work done on the gas. Okay, so that we basically already know how to do. And the change in internal energy of the gas, that's new. And the heat transferred to the gas. Okay, let's see how we do that. All right, so key values, 4 moles, all right? And then our pressure at point A, our volume at point A, our pressure at point B, and our volume at point B. Okay? And our formulas that we're going to use is we're going to use change in internal energy. For an ideal gas is 3/2 nRT. This was given in a previous lecture. We're going to use the ideal gas law itself, and we're going to use the first law of thermodynamics. This is really our tool belt for many of our problems. Not that we always need all three equations, but these are always the things that we want to consider. Okay? Internal energy formula, ideal gas formula, and first law of thermodynamics. Okay? So for part A, we're simply going to acknowledge that the work done on the gas is the negative of the area of the PV diagram, negative because the gas is expanding. And so then we just numerically find it, put our negative in front, and we get a negative 35,000 joules. Okay? That's the work done on the gas. So in other words, the work being done by the gas is positive 35,000 joules. Okay? Good. Then for part B, when we're trying to find the change in internal energy, for this one we need to find temperature A and temperature B. Because only then can we actually use this formula. Because this seems like the natural formula to find change in internal energy. After all, that's what it is. Okay? But it requires a temperature terms, and we don't know them yet. We just know pressure and volume terms. So that means we're going to need to use the ideal gas law twice. All right? So we use the ideal gas law at point A, and we find that the temperature there is 301 Kelvin. And then we use the ideal gas law at point B, and find the temperature there is 2,255 Kelvin. Right? Big temperature increase. Right? And the way we did that is we just acknowledged that we know everything else. We know N, we know P, and we know V, and obviously R is a constant at each point. Okay? All right, there we go. So then we can just plug in our newfound values into the formula for the change in internal energy of an ideal gas. All right, plug in our numbers, and there we go. We get 97,500 joules. Okay? Wonderful. All right, in part C, now we want to find the heat transferred to the gas. Well, since we know work, all right, and we know change in internal energy, then we can just use the ideal gas law to find the one missing. And not the ideal gas law, excuse me. We'll use the first law of thermodynamics. And that's really one of the best times the first law of thermodynamics comes up, is once you know the other two expressions, then you can find the third energy expression quite easily. All right? So then we'll say, okay, so change in internal energy is equal to the heat flow to a gas, because this is always Q2. Q is always Q2. It's never Q from. It's always Q2. Is then going to be the change in internal energy plus the work done by the gas. I'm going to go ahead and replace work by with negative work on, because you can always do that. Okay? You can always make that substitution. And so then I'll just take my change in internal energy and then minus the work on, which is just the minuses cancel out. So then we'll end up adding them together. And there we go. We get 133,000 joules. That's how much the gas heats up internally. Okay? So that's basically, that's related to its temperature change, which we already found. All right? This is the actual increase in internal energy of the gas. And why is that? Why is it such a big increase in internal energy? Well, that's because it both heated up, because we crossed isotherms, because remember isotherms are like this. So we heated up and we expanded. So heating up and expanding definitely means that things are going to get warmer inside. Okay? All right, so good. We got our two general cases out of the way. Let's get on to the examples that actually involve the named thermodynamic processes. All right, so example 3. All right, a balloon contains 5 moles of an ideal gas. As energy is added to the system by heat, such as the balloon heating up in the sun, the volume increases by 25%. Maybe you've seen balloons do that. They get warmer, they get bigger. Sometimes they'll pop in the sun. But they're going to do it at constant temperature. And that's actually a reasonable assumption, that the balloon would be heating up at constant temperature, because the thin membrane of the balloon would allow it to remain at equilibrium with the outside air temperature. So then, it just always stay the same temperature, okay? It would get bigger, okay? But it would actually remain the same temperature, okay? And that temperature in this case is 27 degrees Celsius, so a hot day. So we're going to find the work done by the gas in expanding the balloon, and the heat transferred to the gas, and the work done on the gas. So basically find all the terms in the first law of thermodynamics, okay? So to find the work, we just start off by, acknowledging this is an isothermal process, okay? And we know that because we saw that it remains at constant temperature, so you look for that key term. All right, so that means that your change in internal energy has to be 0. So one of the 3 terms in the first law of thermodynamics is 0 right away. So we can rewrite the first law of thermodynamics as 0 equals Q minus work by. And this is the kind of stuff that shows up in this table here, right? So this would be a good reference here for something like this is this. See? That's basically what I'm drawing on here. All right? Okay. So then we know that the work done on is equal to the negative of the work done by, which then is just equal to the negative nRT natural log of V final over V initial. So now we're just ready to plug everything in. All right, so we'll plug in our 5 moles, plug in our ideal gas constant, plug in our constant temperature. Make sure to convert it to Kelvin. This will give you the wrong number if you leave it in Celsius. Notice I converted it to Kelvin. And the conversion would be 27 plus 273. Okay, that's how you convert 27 Celsius to 300 Kelvin. All right, and then we take the natural log. Now, we were never given a volume. We weren't told that the balloon started at a certain number of cubic centimeters. We don't care because we were given the increase. And that means that when I look at this ratio, I can write the final volume as 1.25 times the initial volume divided by the initial volume, which means the initial volume, whatever it is, just cancels out. So we just end up with the natural log of 1.25. Okay? And when we calculate that, the negative sticks around. So that means that the work done on the balloon is negative 2,800 joules. Thus, the work done by the balloon is positive 2,800 joules. And that makes sense because the balloon is expanding. So it must be doing positive work. Okay? Makes sense, right? All right. Part B, then we want to find the heat transferred to the gas. Well, since it's isothermal, we know right away that Q equals work by. Oh, that's easy. That means it's just the same number, 2,800 joules. All right. And now what about the work done on the gas? Well, the work done on the gas, we actually already know, is just the negative of whatever the work that the gas does. So it's just negative 2,800 joules. Okay? Wonderful. We're done. All right? So there's an example of an isothermal process. All right, now let's move right on to a process that involves constant volume, a isovolumetric. Okay, so we got one example of those. A container of hydrogen contains 13.3 moles of a gas and is cooled at constant volume from 31.5 Kelvin to 1,200 Kelvin. How much heat flows to the gas, and is the heat gained or lost by the gas? All right. So for constant volume, the work is 0. See, so usually something's 0, right? And so that means that the change in internal energy is just equal to the heat added to the system, okay? All right, so then we have then the change in internal energy is equal to Q2, all right? And then we know that change in internal energy is equal to 3 halves nRT, all right? nR delta T. And so we'll just plug that all in. We know we have 13.3 moles, we know the ideal gas constant, and we know our temperature change was this, okay? We know we started at a high temperature and we finished at a low temperature. So that means that our change in internal energy must be negative, okay? It's negative 2.43 times 10 to the 4 joules, all right? So negative 24,300 joules. Okay, well, that means answering part B is pretty straightforward because this is obviously a decrease in internal energy. If you have a decrease in internal energy, that means your Q2 also must be negative. If you have a negative value of heat added to, that means that's the same as heat being lost. So the heat is lost, clearly, okay? Hopefully that makes sense, right? And you can just see, I mean, if you have constant volume and your temperature is decreasing, then you're losing heat, all right? But we really showed it, all right? Hopefully it matched our intuition. Now, let's get on to systems that have constant pressure. We're going to do 2 examples of those. So here we have an ideal gas that has an internal energy drop of 450 joules, all right? 4,500 joules. And while 7,500 joules of energy is expelled from the system. So we have internal energy falling and we have heat leaving. So it sounds like this system is kind of contracting and cooling, okay? And we want to find the change in volume if the pressure is held constant at 101,000 pascals, which of course is 1 atmosphere, okay? All right, so how would we set that up? All right, so first acknowledge it's an isobaric process because that way you can reference the appropriate formulas on either of the tables. And so this is the one where nothing zeroes out. Okay, this is the one common process where none of the 3 energy terms in the first law of thermodynamics is a 0. Okay, so in many cases it's the one that kind of requires like the most steps to it. Okay, so we got delta U equals Q2 minus work by. All right, and we know that work by. The nice thing about isobaric processes, the saving grace of them, is that the area under the curve is a rectangle. So then it's just whatever the pressure value is times the volume change. Okay, so that's going to be helpful. All right. And we know that work by is going to be greater than 0 if the final velocity is greater than the initial velocity. Okay? Now that makes sense, okay? Because it's expanding, all right? And so then we're going to have the change in volume is just going to be Q2 minus the change in internal energy divided by whatever the constant pressure is, in this case 1 atmosphere. All right, and then we just plug in our numbers. Our signs are very important here, okay? And so then we get a volume decrease. And that definitely is kind of what we expected because this system is losing energy in every way, right? It's cooling and it's leaking energy, right? So that it basically, if it's going to keep its pressure constant, it better shrink. And indeed it does shrink. It shrinks by negative 0.0 297 cubic meters, which doesn't seem like a lot, but if we convert it to cubic centimeters, or liters for that matter, we find out it's 29.7 liters of contraction. So it's actually pretty significant, all right? All right, good. We're in good shape, all right? So that's an example of an isobaric contraction, okay? Now let's do a concept question. Now this concept question, unlike the first page where I accidentally drew the curve wrong, and again, I'm gonna fix that on the upload, here we have the correct curve for a isobaric contraction, okay? An isobaric expansion. So let's go through here, because in this concept question, we want to identify paths A, B, C, D in the figure as isothermal, isobaric, isovolumetric, and adiabatic, okay? So do this right now. Pause it and see if you've internalized, pause this video, and see if you've internalized this information enough to be able to label them without looking back. And then, if you're stuck, then look back or hit play. But see if you can do it. See if you can figure out which is which, okay? Some will be easier than others. All right, let's do it. So A is isovolumetric. That's easy because volume remains constant, it's a vertical line, okay? B is adiabatic, okay? It's because B crosses isotherms. And notice here that because it's expanding, because it's going in the direction of increasing velocity, it goes from a higher temperature T3 to a lower temperature T4. So it cools as it expands because it has to, okay? Because it's not losing heat energy, the only way it can expand is by giving something up. The only thing it can give up is internal energy. If it gives up internal energy, it must cool. That's why adiabatically, expanding means you must cool, okay? And then we've got an isothermal process, which is C. We can tell that because it stays right along an isotherm, along one of the blue lines, okay, which represent constant temperature, 4 of them shown as examples, all right? And then D is isobaric because it remains a constant temperature, or constant pressure, and it's a horizontal line, okay? And then a quick note about adiabatic, it is always steeper than isothermal since a change in internal energy will always be less than 0 for expansions. And again, consider the first law of thermodynamics, an idea that since Q is 0 and you're expanding, then you have to give something up, you have to cool, okay? All right, now let's do another example of a isobaric process. So a chamber contains 5.55 moles of an ideal gas. It's held at constant pressure. So there's our key word, isobaric. The initial volume and temperature of the chamber is 77.7 liters and 144 degrees Celsius. Okay? If the temperature of the gas is then increased to 205 degrees Celsius, how much work did the gas do on the environment? All right? And then how much heat flowed into the gas in the chamber? And what was the change in the internal energy of the gas? All right? So basically all three of the terms in the in the first law of thermodynamics. All right, so isobaric process, thus there's going to be our expression. All right, and we're going to use the ideal gas law to get started. PV equals nRT. And then we know, since N and R are constants, that T, the ratio of T over V must be a constant. So going from the first point to the second point must be a constant. All right, they have to be equal to each other. And that means we can solve for the final volume, because notice the final volume wasn't given. We're given both the initial and final temperature, but we're only given the initial volume. So we're going to go ahead and solve for the final volume, because we'll need that. All right, and so it ends up being just the ratio of the temperatures multiplied by the original volume. And notice I convert the temperatures to Kelvin, because I have to. I also converted the original volume to cubic meters. That way I'll be in base units as I do further calculations. And there is the final volume in cubic meters. Okay, and definitely it's larger, because the system expanded. Okay, this is isobaric expansion. We know it's isobaric expansion because you can't go up in temperature without expanding. Think about the PV diagram. All right. So thus the work being done by our gas, by our substance, is just pressure times change in volume. So then it's just going to be nRT over V times delta V, because I've just replaced pressure with nRT over V. Okay. And that's because I wasn't told the pressure, but I don't need it because I have everything else. All right, and I plug in all my numbers, and there we go. We have a work being done by the gas. All right, how much work did the gas do on the environment? 2,810 joules. Wonderful. All right, so that's A. Okay, in B, we're going to find the heat added to the gas. Well, that's just going to be the change in internal energy plus the work being done by the gas. Okay, we already know work done by, okay, because we solved it as the area under the curve, which is a rectangle, so just pressure times delta V. All right, and again, we found pressure with the ideal gas law, and we found T with the ideal gas law. And then we're going to use the formula for the internal energy of an ideal gas. And we already know our temperature difference, so we're all set here. And we know that value, so we can just plug everything in. All right, and we get 4,000 or 45,000 joules. Okay, so a lot of heat is added to the system. The system isn't doing that much work considering how much heat is being added. So where's all that excess energy going? Well, it must be going to heating up the gas itself. So this is kind of inefficient if you think about it. You're adding a bunch of heat to the system. You're getting a little bit of work. Mostly you're just heating up the gas. Okay, so if work is what you wanted, well, you're not doing it the best way. Okay. But that's true of isobaric processes. They're not the most efficient way to get work out of adding heat to something. All right. So in this case, we would just take the heat to minus the work by, and that then is going to give us our increase in internal energy. Positive, so we know it's an increase, and it's 42,000 joules, 42,200 joules. Okay. Hopefully that makes sense. Looks good. All right. Last example, the final process that we haven't done a numerical example for, a adiabatic one. Okay, so an ideal gas is compressed adiabatically from a pressure of 6.67 times 10 to the 5 pascals, so about 6 atmospheres. Okay, so 667,000 pascals. Okay, but it's compressed from that pressure, and it has a volume of 134 liters to a final volume of only 99 liters. And then the question is, how much work is done on the gas? Okay, all right, so let's think about how we'd approach this. So first of all, we're going to acknowledge it's an adiabatic process, which was just told to us. It could, another version of the problem might say a process occurs with no heat exchanged. That would also be code for adiabatic, right? Because Q equaling 0 means adiabatic, okay? For the adiabatic condition tells us that the product of pressure times volume to the gamma power is a constant. So in other words, that means that some pressure times some volume raised to that power is equal to some other pressure times some later volume raised to that same value. And remember, gamma is just a number, okay? It's, let's see, the number escapes me. It is 5/3, okay? For an ideal gas, it's always 5/3, the adiabatic index. All right? So there we are. Oh, wrong page. There we are. Okay, so we're going to use this to find our missing piece of information. Because if you think about it, we know the initial pressure, we know the initial volume, and we know the final volume. So what are we missing? The final pressure, kind of like in the previous example, okay? So then we're going to find the final pressure. Of course, there we're missing the final volume, but here, same sort of idea. We're missing one of the values. So basically we have one equation and one unknown. So we'll solve for our final pressure, plug in our numbers, okay? So I'm going to do here. And we get that it's basically 10 atmospheres. It's 1.1 times 10 to the 6 pascals. See, I'd say it's 1 atmosphere if this was 10 to the 5, but this is actually 1 million pascals. So this is some very high pressure. Okay, looks good. Okay, all right, and that makes sense that it was compressed and the pressure goes up, right? If you're going from 134 liters to 99 liters, it makes sense that the pressure should go up if no energy is entering or leaving the system. Okay, so then we're just to find the work done on the adiabatic system, we'll simply use the formula. Okay. And our formula here is going to have the leading negative because it's the work done on the system. Notice that the formula I gave, I'm going to flip back to the key formulas again. The formula I gave here was the work done on the ideal gas during adiabatic expansion, okay? And that's what we're talking about here as well. This is the work done on the gas, okay? All right, and so then we'll plug in our values and we get a positive value of 30,000 joules. Okay, now does that make sense that work done on the gas should be positive in this context? Well, yes, absolutely, right? Because it's being compressed. It's not doing work on the outside world. If it's being compressed, that means the outside world must be doing work on it. Okay, so absolutely this must be a positive value, and indeed it is, so that checks out logically. Okay, all right, so that's it for our introduction to the first law of thermodynamics and common thermodynamic processes. We're going to use these in the context of something called heat engines in the next lecture. Thank you so much for watching. I hope this lecture was interesting and informative.